equal here is going to have a letter at the bottom, and it's going to be equal to a number. Typically, I is used, but sometimes other letters might be used. It is, but they use I a lot here. It does not mean imaginary here. So, I imagine this sort of stuff definitely shows up a lot in some coding, because there would be a lot of things you would want to do repetitively with different numbers. So you are doing the summation. Does Python use the symbol here, or they use?
No.
They use Right. Right. Yeah. It does. Yeah. It stands for index. Although I agree that since it also is the square root of -1. I might should have came up with another word for index. Yeah. But you can occasionally you will see a different letter there. But I is used a lot. So an N is your upper bound, or where you stop, right? So basically 1 is where you start, N is where you stop. And so if you just had like A sub I, this would mean to add together A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, all the way till you get up to whatever A sub 1 is. Right? So, questions thus far? I does not always equal 1. But most everything we're going to look at, I is going to equal 1, because if I does not equal 1, it makes it much more difficult to do. So, especially whenever we're talking about using the shortcut rules that we're going to see in a little bit. So, you can see I've got like 2 examples here. This one does not start at 1, but most of the ones we're going to see are going to start at 1. So if I have the sum from 1 to 6 of I, then all this means right here is that you're plugging in integer values from 1 to 6 for your I, and you're adding them together. So this would be 1 plus, then you change your I to a 2, then you change your I to a 3, and then a 4, and then a 5, and then a 6. All right, so it's just adding up the numbers 1 through 6 is all that we get here. And for that, 15, 21, we get 21. Okay, so that would be your like most straightforward sort of formula that you would see. Let's look at number 2. Okay, number 2 tells us to start at 0 and end at 5, and our formula is I plus 1, not just I this time. So that would look like this: 0 plus 1, 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, and 5 plus 1. Now, what's that going to equal? 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is what we just did, which is 21. All right? So those two are equivalent to each other, but their formulas and the way that you would like go through them logically are different. If we were spending a lot of time on this, all of our shortcut rules are going to be with I equals 1, so we would talk about how we could convert these to be the same if we were spending longer on this, because we generally want to have ones where I equals 1 for our shortcut rules there. But we're just getting a feel for using this notation is all we're really doing today. So some of the questions you'll have will just ask you to evaluate, and the best way to do this is just like the brute force method of just plugging in the numbers and adding them together, right? Because adding the numbers from 1 to 6 is not going to take you very long to do. Now, if that was from, if we had a more complicated formula and it was 1 to 1,000, we would not want to do that by hand, right? Let's just do a few more here, just basic brute force sort of method where we're just plugging in the numbers. So here we got a different letter this time. You'll see some that maybe have a different letter. So we got j equals 3 of j squared from 3 to 7. So we're going to go, for that we'd have 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. All right, so 9 plus 16 plus 25 plus 36 plus 49 is going to be, it says 57. 135? Somebody check me on that. Trying to improve my mental math skills, but a little shaky. Yes. Yeah. Yeah. This is summation. Like that. That means the sum of. So is always added together. Yes. Now you may see something like on this next one, there's going to be subtraction within the formula, but still between each term, it's always addition. Okay. So like if we have this one here, we're going from 1 to 4. Our formula is 6i minus 2. So we would have 6 times 1 minus 2 plus 6 times 2 minus 2 plus 6 times 3 minus 2 plus 6 times 4 minus 2. Right, so this is going to give us 4, 10, 16, and 22. And we will get 52, I think, for that one. Okay, questions? Mm-hmm. Correct. Right. That's your, so you can think the bottom is your start number, the top is your stop. You stop whenever you get there. All right. Okay. So let's look at this. These are, we're going to start looking at some shortcut formulas. So I really should have, of course, you've got it printed, so it doesn't matter if I hide that or not. So I think this is always confusing. This is confusing with several things. It's even confusing with limits. I've got k equals 1, and I'm going up to 3, and I'm adding 5. There is no k here, right? So I'm not plugging the numbers in. So I've got 5. This one right here is whenever k equals 1. But that value doesn't change because there is no k in my formula, right? And so the next one, whenever k equals 2, I still get 5, right? And then whenever k equals 3, I still get 5 right here, right? So 5 plus 5 plus 5 is going to give us 15. So a shortcut for this, and let me think. I don't think I put these on the actual test. This is like something we've got to learn so we can understand limit definition of this, so we can understand why in the world this all kind of works together. So, so I don't think these problems necessarily are actually on the test. It's kind of like limit definition of a derivative. There's a way they can word it, but there's not a lot of that on there. So, so I don't think you're going to need a note card with this, but I might need to look back through and make sure of that. They occasionally will put something like this on the AP exam, but it is very rare. Like lots of years it's not on there at all. So, so it is okay with me. Like if I give you this, I will let you have these formulas here. So as you do your homework and stuff, keep your notes nearby. You can use these formulas here. So the shortcut that you can use here, it is important for these, our shortcuts, I has to equal 1. If I equals a different number, the shortcut would be different. So if we were going from 7 to 10, my shortcut would be different than going from 1 to 10. So all these shortcut rules are for whenever I equals 1. So if C is a constant, then the sum from 1 to n of C is just going to be C times n. So like on this one here, the sum from 1 to 3 of 5 is just 5 times 3, which is 15, right? So as long as your I or your index right here is 1, you could just multiply these two together if you just have a constant. Okay. All right. So that is a shortcut formula that we can use. I don't know why they're, oh wait. Okay. Oh gracious, I might need to, okay, I'm gonna give you a proof of this. All right. For this formula. All right, I know that there was a mathematician, I can't remember which one, somebody important, obviously so important that I remember their name well. They were asked to add together the numbers 1 through 100. And if you add together the numbers 1 through 100, you know, obviously you could do 1 plus 2 plus 3 plus 4. Whenever a small child was asked to do that, I'm sure that most of them would just say 1 plus 2 plus 3 plus 4 plus 5 and try to figure it out that way. But if we're adding numbers 1 through a value, let's think of this strategy. All right, so what we're trying to do summation-wise is we want to find the sum from 1 to 100. Okay? I'm going to do it first with numbers, and then we'll look at it with an n. So that means I would do 1 plus 2 plus 3 plus dot, 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 plus 99 plus 100. Still left the middle out, and it'd be 1, 2, skip a few, 99, 100. Kids like to do that sometimes. All right, so that is the sum from 1 to 100, right? Is it okay for me to write it also like this? Actually, I do need to, let's leave that 3 out for these purposes here, just so it, would I get the same value if I start with the highest number and work down to the lowest? It'd be the same value, right? Okay. What happens if I add these together? Okay. So if I add sum plus sum, that gives me 2 times the sum from 1 to 100. Correct? Okay. All right. So what is 100 plus 1? 101. What is 99 plus 2? 101. Dot, dot, dot. What's 99 plus 2 here? 101. 100 plus 1, 101. You just keep getting 101 over and over and over again if you do that, right? What we're going to end up with is the sum, 2 times the sum from 1 to 100 is going to be 101 times, how many times is that going to be? Times 100, right? Because there's going to be 100 values there in our list. So this is our sum, this is twice our sum from 1 to 100, right? This will give us double that amount. So if I want to find just the sum from 1 to 100, I could divide both sides of this equation by 2, and the sum from 1 to 100 would be 101 times 100 divided by 2. Which would be 50 times 101 would be what? 50. Imagine being a small child. I need to figure out which mathematician. It might be like a fable, sort of like George Washington chopping down the cherry tree or something. It is, yeah. All right, so let's think about this not for the number 100, because this is specific to the number 100. Let's think about this as the generalized formula, okay? Same. So this is the proof of what we're about to do. So from 1 to n. The sum from 1 to n would be 1 plus 2 plus ... plus, my last number needs to be n. What would be the number before n? N minus 1. All right, so that would give me the sum from 1 to n. So if I write that again, but put it in backwards order, I've got n plus n minus 1 plus ... plus 2 plus 1. Okay, and if I use that same logic that I was using before, add these together, so I've got 2, the sum from 1 to n of, what do I get whenever I add 1 and n? N plus 1. What do I get whenever I add 2 and n minus 1? N plus 1 again. Okay. ... N minus 1 and 2 gives me n plus 1. N plus 1 would be n plus 1. Alright, so how many times am I adding n plus 1? N times. Alright, so like over here it was 100, so this was 1 to 100, so it was 100 times. Here, I don't know what number n is, but n's where I stop, so it's going to be n plus 1 times n. So this is going to equal n times n plus 1. And then if this is twice the sum, so if I divide both sides by 2, the sum from 1 to n, I should be putting an I right here on all my sums. This is wrong without the I. Because it's got to be a sum of something. All of these should have I's. The sum from 1 to n of I is going to be n times n plus 1 over 2. So Connor, you said you were multiplying the middle two numbers together, right? Yeah, is that what you were saying?
I like Milton's number for 8 and 9.
Okay. I'm trying to think how that relates to, because it would be,
like if you have 100 and up to 100.
Right. Right. So this is a shortcut rule. So anytime you have to do the sum from 1 to a number, you could use this shortcut rule. So if we go back to the example we had before, if I need to do the sum from 1 to 6 of I could do 6 times 6 plus 1 divided by 2, which would be 6 times 7, which is 42, divided by 2, which is 21. Now, it's probably not that much faster for just going from 1 to 6, right? But if I needed the sum from 1 to 275, right, the shortcut rule would definitely be faster than typing into your calculator 1 plus 2 plus 3 plus 4 plus 5 all the way up to 275. Plus, if you're typing that manually into a calculator, you're probably going to mess something up between 1 and 275. But if I want to do the sum from 1 to 275 of I could just do 275 times 276. Oh. Divided by 2. And then you'll get an answer for that we need to use the calculator for. So, again, like the difference here in the way that you do these problems, you can do this doing 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. Sometimes it's easier just to do it that way. Or you could do 9 times 10 divided by 2, which would give you 90 divided by 2, which is 45. Right, so you can use that shortcut rule for that. This one would also be 45, obviously. Now, this stuff I'm doing up here is the proof for this, because mathematicians, if they come up with an idea, they have to prove logically that it is true. You can't just say, I feel like this should be the case. Let's all do this, guys. I mean, you can. If you can't, there are some things that are way beyond my reasoning that, like, we generally use as truth, but have not been officially proven as far as mathematics go. But most of the mathematics that we use has been proven in some sort of way before. So if you're majoring in math, get ready for some stuff like this right here. There will be a lot of it, which is pretty cool, but also confusing sometimes. All right, so we are not going to do the proofs for I squared or I to the third, but these are the shortcut rules for I squared and I to the third. So, if I have to do this particular sum that I have here, when I look at this particular sum, I've got the sum from 1 to 10 of I plus 1 over n squared. The n, what is my n for this problem? It's a 10, right? So I could plug that in as my value there. So you have the option of doing it the long way, which would be 1 plus 1 over 10 squared plus 2 plus 1 over 10 squared plus 3 plus 1 over 10 squared plus dot, 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 until you get to 10 plus 1 over 10 squared, right? I think it's pretty easy to understand what you're doing there. Like, that makes a lot of sense to me, just to write it out like that. But as far as, like, typing it into the calculator and getting an answer, it's strenuous. And you also have to keep in mind that we're trying to get in the mindset of ancient mathematicians that did not have calculators to use for this. So, like, if they wanted to do that problem right there, they would have to do every bit of it by hand. So you can see why the shortcut rules would be so appealing to them, because it drastically reduces the amount of calculations that they have to do. So first of all, that n right there is going to be 10, right? It is not an I. It's not the number that is changing. So if we want to think about this, we could think about it like this: I plus 1 over 10 squared, right? Which, of course, is the sum from 1 to 10 of I plus 1 over 100. So if you think about doing this, that 100 is going to be in every single term, right? We could even think of it like this, 1 to 10 of 1 over 100 times I plus 1, like that. Those are equivalent. So, much like derivatives, if I have a coefficient right here, I can just pull it out front. Okay, so the way that I can think about this is I can do 1 over 100 times, I can take the sum of my I and my 1 separately. So I'm thinking of it like this, my sum from 1 to 10 of I plus my sum from 1 to 10 of 1, right here. Okay, so here's where my shortcut rules can come in. The shortcut rule for just the I, the sum from 1 to n of I is n times n plus 1 divided by 2. Right? So for this one, n is 10, so it would be 10 times 10 plus 1 divided by 2. When I have a coefficient, like a constant right here, I don't have a variable, what is my shortcut rule there? That number times n, which is 10 here. So it would just be 1 times 10. And you especially think about like life without a calculator, because these mathematicians would not have had a calculator. I realize you do, and that's why we're not going to spend a ton of time on this. But 10 times 11 would give us 110. Divide it by 2, you'll get 55 plus 10. So you get 65 times 1 over 100 is going to give us 0.65. Say that again. You could do that, but shortcut rules that I have here only work if I equals 1. So like if you change that sum, it would be true that this sum could be just the sum from 2 to 11 of I over 10 squared, but, or 11, well, it'd have to still be a 10 squared there. But if you change your index, the shortcut rules do not work for I if I equals 2. So in general, you want to keep it with I equals 1. Does that make sense? All right, so, here's one that's a little bit more difficult because it has a square. And I'm not going to make you memorize the shortcut rules for the squares because I don't have them memorized myself. The shortcut rule for I squared, give it to me, what is it there? Okay, I'm going to do this for you also. Let's go ahead and multiply this together. N times n plus 1 would be n squared plus n, and then 2n plus 1. So if we distribute that, we get 2n to the third plus n squared plus 2n squared plus 1. So that's 2n to the third plus 3n squared plus 1. So this is also equal to 2n to the third plus 3n squared plus 1, because depending on what we're doing, sometimes it is easier to use the first formula, sometimes it's easier to use the second formula. It just depends on the case. You're right, it should be an n. That should be an n there. Thank you. Okay, so if I have the sum from 1 to 15 of n times I squared minus 1. First of all, this n right here is going to be 15, right? And coefficients, we can pull them out. So we've got 15 times, I'm going to write the sum just so you guys are seeing this. If you skip this step, it's fine. The sum from 1 to 15 of I squared minus the sum from 1 to 15 of 1. So shortcut rules tell me that I would be doing, the shortcut rule for I squared would be 15 times 15 plus 1 times 2 times 15 plus 1 over 6. And then my shortcut for a constant is just that constant times my n. Like that. And in the olden days, you wouldn't have a calculator, but since we do, we are going to use it because there's no sense in making our life so difficult. So 15 times, actually let me just see, 15 times 16 times 20 or 31 divided by 6, we're going to get 1240, so 15 times 1240 minus 15. You can put the whole thing in at one time if you want. I get worried with my parentheses, so I do it piece by piece a lot of times. And we get 18,375. Okay. Also, let me show you this. Your calculator will do a summation. I do not want you just typing this in using the summation. I want you to write it out, use the shortcut rules, or you can do it the long way where you're doing like 1 squared minus 1, 2 squared minus 1, 3 squared minus 1. I would not suggest that on a problem like this because it's going to take you a very long time to type it all in, and you might mess up doing that. But I do not want you using the summation to get the answer, but you may use it to check. So, is it under 3? Yeah. If you do F3, which is calculate, if you go down here to number 4, you got sum, and you would type in your formula, which we would go ahead and plug in that 15 times, I don't think we use the I in the calculator. I think we need to use the X, but I'm not 100% sure. I can't remember. Okay. So you're going to type in your formula, and I believe it's comma X, comma 1, comma 15. Let's hope it works. It's been a while since I did this. Yes. I think you can use the other variables besides X if you want, but I'm not sure if it does it right if you use I. So you can check your work on the calculator. I just don't want you doing it like this for every problem because these shortcut rules are what we're going to have to do our limit definition. Like we need those for what we're going to do. So I want you using those. All right. So a lot of your homework is just going to give summations and ask you to find the value. Some of them are going to be like the easiest, just to do 1 plus 2 plus 3 plus 4 plus 5. Others, you might want to use the shortcut rules. For the shortcut rules, you must have I equals 1. If I does not equal 1, you're going to have to do it by hand. Then you are going to have some questions like this that ask you to write these with sigma notation. Okay? So if I want to write this with sigma notation, this is just the sum from 1 to 7 of I. Right? So you want to look at the value that's changing and going up by an integer. So 1, 2, 3, you just have an I right here. So if I look at the second one, I've got 4, 5, 9. My value that's changing is this value right here. That's going to be my I, right? So I would have, the formula would be the sum, actually, the sum of I squared plus 1. What's the start value for that? What? 4? And it goes up to 9. Right, so that one doesn't have a start value of 1. It's not asking you to evaluate it. It just wants you to write it in sigma notation. I think the ones like these are kind of hard to do. What is your I in here? What's the value that's changing? The number over n. So this number right here becomes 2, and then it becomes n, right? So everything else in your formula stays there. You're going to have the sum of 1 over n times 6 plus the value that's changing, this 1, 2, 3, 4, 5, n right here. That is your I over n. Right, so that value that's changing, the position that it's in, is the one that's going to be replaced with the I there. Where do we start at for this one? 1. Where do we end? N. In front, yes, you may. You can write it like this, 1 over n, sum from 1 to n of 6 plus I over n, like that. You can do that. So for that last one right there, what value is changing? The number over our n squared for that. So this one would be the sum. That value starts at 1 again. It goes to n. Oh, excuse me. Of n times the square root of 1 plus I over n squared. That's how we would write that with summation notation. So, your assignment, it's not here, it's on Canvas. Is from your book tonight. It's 1 through 23 odd on page 299. Okay, it's just going to be practice with the sigma stuff. You can use your calculator to, like, do out the operations, but only use it to check with your sigma notation. I don't want you to just, like, type all the sigma ones in and say it equals 1283. And when the bell rings, you are going to go to second period and drop off your book bags. I think they're going to do announcements, and you're going to wait for that. Yes.
Doing what?
Use the experiment.
Let's not do it today, but maybe we can do that one day.
Okay.